EV and PHEV battery chargers. The battery charging system is a critical part of electrical vehicles and plug-in hybrid electrical vehicles. The efficiency, charging speed and cost of such chargers are crucial to the commercialization of the plug-in hybrid electrical vehicles. There are many different topologies are available for battery chargers. Due to safety requirements and standards, most battery chargers are required to be isolated from the AC electric grid. In some cases, bidirectional power flow is necessary in order to realize vehicle-to-grid functions. A survey conducted by the US Electric Power Research Institute (EPRI) revealed that 78% of the US population drive 40 miles, 64 kilometers or less their daily commuting. Therefore, PHEVs capable of a 40-mile electric driving range can be significantly reduce gasoline usage in passenger vehicles. For a typical passenger vehicle, the average energy consumption is approximately 150 to 300 watt-hour per mile. To achieve a 40-mile electric range, a battery that contains general energy of 60 to 12 kilowatt-hour is approximate. Lithium-ion batteries are considered as the only available energy storage solution for the PHEVs at the time being. To achieve safety and reliable operation while maintaining the cycle life and healthy of the batteries of the PHEVs, the typical available energy from the lithium-ion batteries is approximately 60 to 70% of the nominal capacity. Therefore, 10 to 16% kilowatt-hour lithium-ion battery pack is very typical in many PHEVs under development. The battery on board of a PHEV needs to be charged from the grid through either an on-board or off-board charger. For private vehicles, these PHEVs will be charged at home or a public charge station through either 110 or 220 volts AC input. In order to make sure that the vehicle is ready for use by the second morning, the battery must be fully charged within a reasonable amount of time, typically 2 to 8 hours. In the past few decades, various charging circuits have been developed targeting different applications such as laptops, computers, portable electronics, and uninterruptible power supplies (UPS). Isolation is one of the basic requirements for all battery chargers for safety. The charging current is generally controlled by continuous feedback of critical battery parameters such as battery voltage, the SOC, temperature, and so on. As far as the unidirectional charging system is concerned, chargers based on flyback and forward converters are typically examples for low power applications. Both topologies need only on active switch. However, flyback and forward converters undergo high voltage spikes when the excessive energy stored in the leakage inductance of the isolation transformer is exhausted at the turn-off moment. Therefore, at high power operations, an auxiliary snubber circuit is needed. Regardless of the limitations, flyback or forward topologies are being used in PHEV chargers. Chargers based on off-bridge and full-bridge unidirectional DC to DC converters are favorable alternatives to chargers based on flyback and a forward converter. The magnetization of the isolation transformer in a half-bridge converter is bidirectional. Therefore, the demagnetizing circuit is eliminated. The leakage inductance of the transformer, a key parameter for energy transfer. The operation of a full-bridge DC to DC converter is similar to a half-bridge converter. the electrical stress of the semiconductor in a half-bridge or full-bridge converter is significantly reduced. Soft switching is easy to implement in half-bridge or full-bridge converters. The disadvantages of these converters are the increased number of semiconductor switches. Resonant converters can also be employed as battery chargers at extremely low cost. However, resonant chargers generally provide pulsed charge current, such as the case in inductive heating, other than constant current or constant voltage charging. The impact of pulsed current charging on battery capacity and life cycle is not fully understood at the present time. And this slide shows the general architecture of unidirectional PHEV battery charger. It consists of a front-end rectifier, a power pack correction stage, and an isolated DC to DC stage. Forward or flyback converters. This slide shows that circuit and operation of a forward and flyback converter respectively, where capital R is the battery internal resistance, E is the battery internal voltage, and V0 is the output voltage across the battery, including the battery internal voltage and voltage drop across the internal resistance. The operation of a forward converter is similar to that of the buck converter. When switch S1 in this figure turns off, the leakage inductance of the transformer will exhaust all the excessive energy through the switches. It therefore includes the significant voltage spikes across the switches. The energy stored in the magnetizing inductance could be exhausted through an auxiliary winding as shown in this slide. However, the excessive energy in the leakage inductance of the transformer could only be mitigated through a snubber circuit, which is also needed in a flyback converter. In the flyback converter shown in this particular slide, when D1 conducts, the load voltage will be induced in the primary side. Therefore, in the off state of S1, the voltage across S1 is V in plus V0 by N, where N is the turns ratio of the isolation transformer. This indicates that although it may not be necessary to have a filtering inductor in the flyback converter, the semiconductor switch will in fact undergo higher voltage stress. This slide shows a half-bridge DC to DC converter. Switches S1 and S2 are switched with their phase shifted by 180 degree. The leakage inductance of the transformer serves as the component of energy transfer. If the parasitic inductance of the computing loop is negligible, the voltage spikes across the conductor will not be concerned. This slide shows the circuit topology and operation of a full bridge DC to DC converter compared to the half bridge converter, where only half of the DC voltage is imposed on the primary side of the transformer in every switching cycle. The full bridge converter utilizes the whole DC link voltage. Similar to a half bridge converter, the leakage inductance of the transformer in a full bridge converter does not contribute to any voltage spike across the switches. This leakage inductance should be designed approximately for the best performance. Power factor correction stage. A power factor correction stage is generally placed between the rectifier and the DC to DC stage to avoid harmonics pollution to the grid as well as to stabilize the DC link voltage. A typical power factor correction stage circuit shown in this particular slide consists of an inductor L, an active switch S, and a freewheeling diode D. Bridgeless power factor correction circuits have also been used in the battery chargers. Now coming to the decreasing impact on the grid. The AC grid side current with and without a power factor correction stage is shown in this particular slide, where the grid voltage is 110 volts AC and the output power of the charger is 5 kilowatt. And figure shows the power factor correction stage in PHEV charger, and figure A without power PFC and figure B with PFC. It can be seen that from these figures, with the PFC the input current is much better. The current is close to the sinusoidal and current peak is significantly decreased. The impact of harmonic currents on the grid is mitigated. Also, the primary diode rectifier will undergo smaller current stress. The power factor is close to 1. This slide shows the decreasing the impact on the switches. The PFC circuit also helps boost the DC link voltage to a higher level and stabilize the DC link voltage. Therefore, at the same output power, the current through the switches will be decreased to enhance the safety and output capability. This figure shows the switch current at different VE in with the same output power. When V in is increased to 400 volts DC, the switch current is significantly decreased. As long as the voltage across the switches does not exceed the breakdown value, higher DC bus voltage will lead to higher power capability for the same devices used. And in this figure B shows the maximum charging current that the system can deliver. Increasing the DC link voltage will benefit the output capability. Here the maximum repetitive switch off current of the semiconductor switch is set to 70 amperes. This slide shows the bidirectional battery chargers. It is possible to equip a PHEV with a bidirectional charger with bidirectional power transfer capability. The energy stored in a PHEV battery can be sent back to the grid during the peak demand hours for peak sharing of the AC electric grid, or to the supply power to the home and office during the power outage. The isolation can be achieved using high frequency transformers in the DC to DC stage at high frequency level as shown in this particular slide. The isolation can also be achieved using a transformer at the grid frequency level as shown in this figure. It is difficult to add the PFC stage to the bidirectional charges, but the AC side current can be controlled using the grid side inverter to limit the harmonics and improve the power factor. Coming to the other charger technologies or topologies, these chargers are based on single phase low power inputs. In applications such as a commercial transportation and recharge stations, it is necessary quickly charge the battery in a relatively short time. For example, for a 16 kilowatt hour pack, to charge the battery from 30 to 80% SOC in 5 minutes will require 16 kilowatt hour, that equal to 96 kilowatt. Assuming that the battery is able to accept this type of the charging, the charging power will have to be supplied. This is typically done through the 3-phase high power input. Excessive heat may be generated during high power fast charging of EV and PHEV batteries. The high charge rate may also impact the long-term capacity or life of the battery. With more and more renewable energy and distributed generation, the DC grids are starting to emerge. Almost all renewable resources, including solar and wind, can be in the form of DC. If a PHEV is connected to a DC grid, then the battery can be charged directly from the DC source. Traditional chargers designed for AC input can be used to take DC input, but a specially designed DC charger will have no need for the rectifier and PFC stage. This slide shows the inductive charging. The above chargers all need an electrical contact with the electric outlet. This hardwired electrical connection can provide a few cavities. For example, if the cable is pulled out of the electric outlet, When the battery is still being charged, then there could be a spark and potential damage or injury. Another example is if somebody, such as a children, could get hurt if they happen to play with the cards, etc. Charging the vehicle when it is raining could be potentially dangerous. Wear and tear of the plug and cable could also be a source of danger. Hence, inductive charging becomes an alternative. In 1995, the US SAE Electric Vehicle Charging System Group, Japanese manufacturing including Toyota, Nissan, Honda and Destino, together developed the inductive charging started SAE-J 1773. In 1999, SAE-J 1773 was anchored and recommended as an internal standard. GM has already produced electric vehicles adopting inductive charging in GM's EV1 program in the year 1990s. Since inductive charging does not involve direct contact of electricity, it is safe and convenient way to charge an electric battery. The task can even be completed by a child for 50 kilowatt inductive charging. Inductive charging involves an isolation transformer where the secondary winding and core can be removed from the primary. This figure shows the topology used in inductive chargers. This slide shows the wireless charging. Wireless charging involves the use of power and energy transfer at a much longer distance. It is different from inductive charging, which involves a transformer with closely placed primary and secondary windings. Although inductive charging can eliminate the direct electric contact, it still needs a plug, cable and physical connection of the inductive coupler. Wear and tear of the plug and cable could cause the danger as well. Wireless charging could eliminate the cable and plug together. In this scenario, a driver can pull the car over to a specially designed parking lot and the car battery is automatically charged without the pulling of a cable or plug, as shown in this particular slide. It provides the safest approach for electrical vehicle battery charging. There have been a few different experiments carried out for wireless energy transfer. The most compromising technology is using electromagnetic resonance, as shown in this particular slide. In this setup, there is a pair of antennas with one placed in the parking structure as the transmitter and one inside the car as a receiver. The two antennas are designed at resonant controlled frequency. The limitations are the level of power transfer and efficiency due to the large air gap between the two antennas. In this circuit shown in this one, RS is the internal impedance of the source and the resistance of the primary coil. R0 is the load resistance and the resistance of the secondary coil. L1 is the leakage inductance of the each coil and Lm is the mutual inductance of the two coils. There are two ways to make the circuit resonant. If we design the circuit and select the frequency of the power supply V1 such that omega L1 minus 1 by omega C equal to minus 2 omega Lm, and the total equivalent impedance is Z equal to Rs minus J omega Lm R0 by R0 minus J omega Lm. If we design omega L1 minus 1 by omega C equal to 0 and the total equivalent impedance is Z equal to Rs plus J omega Lm R0 by J omega Lm plus R0, then the circuit will be in resonance. However, since both the mutual inductance and leakage inductance change with the distance between the two coils, the frequency will have to be tuned based on distance in real world applications. This figure shows the equivalent circuit during the resonance of the two conditions. And this slide shows the simulation results of the circuit. The first plot shows the two resonant frequencies. The second plot shows that when the distance between the two coils increases, the two resonant frequencies gets closer. Thank you.